Monoidal categories and their representations, Lecture 19, Diagram Categories. We start by recalling the classical Schur-Weyl duality. Let n be a positive integer. Consider the complex vector space C to the power n, which we denote by V. So this is the standard n-dimensional vector space over the field of complex numbers. Then this vector space is naturally a module over the group of all invertible n times n matrices. So n times n matrices act naturally on C to the power n, so on column vectors with n coordinates. Therefore, for any positive integer k, the case tensor power of V is also a module over the same group, via the usual diagonal action of the group on tensors. So if we have an element G in our group, and we apply it to the tensor product of V1, V2, and so on, Vk, so this is defined as the tensor product of G applied to V1, tensor to G applied to V2, and so on. This is the usual Hopf algebra structure on the group algebra of this group. Further, we can also view the case tensor power of V as a module over the symmetric group Sk, where a permutation sigma from Sk acts by permuting the indices of the elements in the tensor product of some vectors. So sigma applied to V1 tensor V2 and so on tensor Vk is defined as V sigma 1 tensor V sigma 2 tensor and so on. So we have two natural actions on the same vector space, and the classical Schur-Weyl duality says that these two actions centralize each other, and moreover, they generate each other's centralizers. So if we consider V to the tensor power k, then the action of GLN commutes with the action of Sk. Moreover, the centralizer of the action of GLN is generated by Sk and vice versa. The centralizer of the action of Sk is generated by GLN. Now let us try to associate to this classical result a certain monoidal category. We will denote this category by curly S. So the category curly S is a free, strict, C-linear symmetric monoidal category on one object. We will denote the generating object for this category by bullet, or sometimes one can denote it just by a vertical line. So this is the generating object, and it's a free monoidal category over it. So all objects of this category are exactly the tensor powers of the bullet, where the power, the exponent of the power, can be any non-negative integer. Diagrammatically, one should write bullet, tensor power bullet, and so on with k factors, but we can also omit the notation for the tensor product and just write this object bullet to the tensor power k as k bullets written in a line after each other. Note that we also have the identity object, which is the zero tensor power of the bullet, which will be diagrammatically represented by nothing. So it just sums in the empty space. So next, we define the generating morphisms in this category. So there will be only one generating morphism, which is called crossing, and this will be the morphism from the tensor square of the bullet to the tensor square of the bullet. One usually calls this crossing the elementary symmetric gradient. Diagrammatically, it is represented simply by crossing. So we read the diagrams from bottom to top. So this crossing starts from the tensor square of the bullet from 2 points, and then we have this crossing which we draw diagrammatically like this. Next, let us describe the defining relations. So this is a symmetric gradient, so if we square this crossing, we should get the identity morphism, of course, on V tensor V. And here is the second relation, which one can recognize as a short braid relation for the symmetric group. So if we have the crossing on the first two components of the threefold tensor product, and then the crossing on the third and the second components, and then again a crossing on the first two components. This should be equal to the composition of the crossing on components 2 and 3, then the crossing on components 1 and 2, and then again the crossing on the components 2 and 3. So these are the defining relations in our category. Sometimes it is very useful to identify the objects of our category C with non-negative integers. And so the k-fold tensor product of bullet with itself can be identified simply with k. And as already mentioned, Sk is the symmetric group on k elements. Then we can describe the morphism spaces between different objects in our category. So our objects are non-negative integers, 0, 1, 2, and so on. And the home space from the object k to the object m is 0 if k is different from m, and it is given by the group algebra of the symmetric group Sk if k is equal to m. So this follows from these defining relations, also combined with the interchanged law in the category S. And now we can think of our Schur-Weyl duality in terms of this symmetric category curly S as follows. We have a monoidal functor phi from our monoidal category curly S to GLN mod, which sends bullet to our module V. And then the object k is sent to V to the tensor power k. And of course, one can consider other monoidal functors from S to other categories to this category and so on, and think about possible other instances of Schur-Weyl duality. So this is an example of a very easy diagrammatic category, this symmetric monoidal category curly S. Let's top up our game a little bit, and let's consider, instead of the general linear group GLN, the orthogonal group. So here is the setup for the second Schur-Weyl duality and the second monoidal category. Let n be a positive integer, and now consider the vector space V, which is r to the power n. So over the real numbers, the standard n-dimensional space over the real numbers. Then V is naturally a module over the orthogonal group On. This is a group of all orthogonal n times n matrices with real coefficients. Now, for any positive integer k, we can again consider the case tensor power of V, and since On is a group, we have a natural action of On this case tensor power of V, which is given by the diagonal action on tensors. So the element G acts on V1, tensor V2, tensor, and so on, as G acts on V1, tensor G acts on V2, and so on. And of course, just as in the previous example, this tensor power of V is also an Sk module, where a permutation acts on the tensor product of vectors by permuting the indices of these vectors. The two actions, just like in the previous case, commute, but the catch is that they no longer generate each other's centralizers. Indeed, in order to generate each other's centralizers, we would need to consider here instead of the orthogonal group, the general linear group. But now, the group which acts on V is slightly smaller, so it is natural to expect that the centralizer on the other side should be slightly bigger. So we need to add something to the symmetric group, Sk. So what exactly do we need to add? So the difference between this example and the previous example is that the second tensor power of V has the trivial module over the orthogonal group, both as a quotient and as a submodule. One can note that V is isomorphic to V dual, and the morphisms from the second tensor power of V to the trivial module and from the trivial module to the second tensor power of V are exactly the adjunction morphisms in the category of finite dimensional real vector spaces. So in some sense, we need to add these elements, so these morphisms, to the symmetric group. To the very least, we need to add the composition from the second tensor power of V to the second tensor power of V, which factors through the trivial module. This is an element which centralizes the action of O and R by definition, but this is obviously a non-invertible element, so this element doesn't come from the action of some group. So this is something extra which we need to add, and we diagrammatically will depict this element by the following diagram. So it's a diagram consisting from a cap and a cup, and we read it from top to bottom. It is also quite interesting to note that the other composition, if you go from the trivial module to V squared and then come back to the trivial module, then from the formulas of how a junction morphism in R mod work, so this composition equals the identity on the trivial module times the dimension of our vector space V. And this information we can use to define our new centralizer, which will be given by the so-called Brauer algebra. So in order to define the Brauer algebra for k elements, we need to define the notion of a Brauer k diagram. So a Brauer k diagram is a partition of two k elements into pairs. This is how we will go to depict this. So we have k elements, k bullets in the bottom and k bullets in the top, and we partition them into pairs. So if two bullets belong to the same pair, we connect them by some line. Of course, this diagram should be read up to isotopy and so on. But here we have a typical example of a Brauer diagram where k is equal to 5. So let K be a field and delta be an element in this field. Then we can define the Brauer algebra B, which depends on our choice of the field, on our choice of the number of points, and our choice of the parameter delta. So this algebra has as basis all Brauer diagrams for our K. The multiplication is defined as follows. We concatenate this diagram, so we put one diagram on top of the other, and then we take the induced partitions for the most upper and most lower points, which is induced by this concatenation. And then we remove possible middle parts, where we compensate by multiplying by delta for each connected middle part which is removed. So here is an example. So here is one Brauer diagram, here is another Brauer diagram. We put one of them on top of the other. We identify the middle points in this way. And now we read through the induced partition between the most upper and most lower points. We will get this. And then in the middle, we have two connected components, this one and this one, which should be removed. And since we have two connected components, we multiply with delta to the power 2. Let us denote by epsilon the Brauer diagram, which looks as follows. So we have this cup and the cap between the leftmost 2 points, and then the rest is just connected as in the identity. It is very easy to see that the Brauer algebra is actually generated by the symmetric group Sk and this one additional Brauer diagram, epsilon. And now we can define the Schur-Weyl duality for the orthogonal group. So let's come back to our setup where we have the natural ON module V and its k's tensor power V to the tensor power k. So as we already mentioned, Sk acts on V by permuting the factors of each tensor product. Let us define the action of the element epsilon on V as the composition V to the tensor power 2, which projects onto the trivial module and then embeds back into V to the tensor power 2, given by the usual evaluation and co-evaluation morphisms in R mod, where we do this for the first two factors of the tensor products, and then we take the identity map on all the remaining factors. One can check that this extends to an action of the Brauer algebra on V to the tensor power k. Note that we don't take an abstract Brauer algebra for some delta, we actually take as delta the dimension of V. So it's a very specific Brauer algebra. And the second version of the Schur-Weyl duality says that the actions of the orthogonal group and of this Brauer algebra on V to the tensor power k, they commute and generate each other's centralizers. So let us now describe an approach to this Schur-Weyl duality via a monoidal category. So let K be a field and delta an element in K. Consider a strict K-linear monoidal category Carli beam with the index delta, which is generated by one object. Again, we can use either bullet or the vertical line. Then, of course, since this is one generating object, then all other objects are tensor powers of these objects. So we have the objects bullet to the tensor power k, where k is a non-negative integer, and we diagrammatically write them as k bullets which are placed on one horizontal line. So in particular, if k is equal to 0, we have nothing. So the identity object is given by nothing. But now we have more generating morphisms. In the previous case, we only had the crossing, and now we have 3 generating morphisms. We still have the same crossing. This is a morphism from 2 bullets to 2 bullets. Then we have the morphism cup, and this is a morphism from the identity object to 2 bullets, and we draw it as a cup. And similarly, we have a cap, and this is a morphism from 2 bullets to the identity object, and this is how it is drawn. So we start from 2 bullets, and at the end we have nothing. So this is a morphism from 2 to 0. And here are the relations. Of course, since we have the crossing, just like in the previous case, we take the same relations for the crossings as in the category Carli S. So crossing squares to the identity, and then we have the short braid relation for the crossing involved in the tensor product of V with itself and with itself once more. Next, we have the following relation for the morphism from 0 to 0. If we start from 0, we can do first the cup and then the cap, and this will be a morphism from 0 to 0, and this morphism should be equal to delta, of course, times the identity morphism on 0. Next relations can be recognized as adjunction identities for the morphisms from bullet to bullet, which use cup and cap as morphisms between the identity object and the square of the bullet. So we have 2 adjunction identities for these morphisms, which can be represented diagrammatically in this way. Next, we also have the absorbing relations, which can be also paralleled with Rademeister moves for knots. So if we apply a crossing to a cup, we get our cup back. And similarly, if we apply a crossing to a cap, we get our cap back. So this is like a Rademeister move for one orientation of the knot, but we also need the same thing for the other orientation. And this can be viewed as the following twisted absorbing relations when we rotate everything 90 degrees. So we start from one bullet, we do identity tensor with a cup, and we go to 3 bullets, and then we do the crossing on the first 2 elements, and then we do the cap on the second and the third element. So this morphism from 1 to 1 should be equal to the identity, and similarly on the other side. Okay, these are not all. Then we also have the so-called twisting adjunction relations, and these are the following diagrams. So we start from 2 bullets, we use the cup to go to the tensor product of 4 bullets, then we do the crossing in the middle, and then we do the cup on the last 2 elements, again to go to 2 bullets. So the composition should be equal to the crossing, and similarly on the other side. And it turned out that these are the relations which you need to define this Brauer monoidal category Carli B sub delta. From this definition, one can deduce that this category is symmetric monoidal. So the symmetric braiding is given by the following diagrams. So this is an example of the symmetric braiding for V tensor squared tensored with V tensor cubed. So this is the diagram which gives a symmetric braiding for this monoidal category. So this category is rigid because we had these adjunction relations which tell us that the generating object is self-dual. So these adjunction identities say explicitly that the generating object is self-dual. And since the generated object is self-dual, then all objects have duals. So this is a rigid monoidal category. This is a rigid symmetric monoidal category with self-dual generating objects. And then the Schur-Weyl duality is a monoidal functor from the corresponding Brauer category, where we now have to evaluate delta to the dimension of V. And this is a monoidal functor to the category of all modules over the group ONR. So in this way, we can view our Schur-Weyl duality using certain monoidal representations of this Brauer monoidal category. Okay, and let us go to yet another Schur-Weyl duality. Now consider our vector space V, which is C to the power n, as a natural module over the symmetric group Sn. So we started from V as a GLN module, then we went to V being an ON module, and now we restricted much further to the finite symmetric group Sn. But again, this is a group, so we can consider the case tensor power of this Sn module, and it is, of course, an Sn module. So the question is, what centralizes this action? Of course, the symmetric group Sk, it still centralizes the action when it acts by permuting the factors in the tensor product of the vector. Moreover, the whole Brauer algebra, BCK dimension of V, still centralizes this action because each element of Sn acts as an orthogonal transformation of this tensor power. And the full answer was given by Paul Martin and Vaughan Jones. The answer is that the correct centralizer on the right-hand side is given by the so-called partition algebra, which is a generalization of the Brauer algebra for the same field, for the same exponent of the tensor product, and for the same parameter dimension of V. So what is a partition algebra? So we define Brauer algebra using Brauer diagrams for K, and partition algebra is similarly defined using partition diagrams for K. So Brauer diagrams where we have two K bullets and we divide them into pairs. So partition diagrams, we have two K bullets and we divide them into disjoint subsets of arbitrary size. And the composition is defined similarly to the Brauer algebra. So now we have a set partition of 2k elements, another set partition of 2k elements, we concatenate them, read through, and potentially remove some middle parts, and for each connected middle part removed, we should pay the price of the parameter delta. And the corresponding Schur-Weyl duality reads as follows. There is an action of this partition algebra on the case tensor power of V, such that the actions of the symmetric group Sn and this partition algebra on V to the tensor power k, these two actions commute and generate each other's centralizers. Let us now try to describe the corresponding partition monoidal category Carly P sub delta. So let K be a field and delta an element in K. We consider the strict K-linear monoidal category Carly P sub delta generated by one object. Again, sometimes it's useful to draw this object as a bullet or sometimes as a vertical line. It simplifies some pictures and we will use this now in the definition of Carly P. Then, of course, all other objects are just the tensor powers of this object bullet, and we draw them diagrammatically either as k bullets, which are aligned on a horizontal line, or k vertical lines, which we draw one after another. Now we have 5 generating morphisms. Again, we read them from bottom to top. So here we have the crossing. This is the original generating morphism already in curly S. Next, we have a morphism split from 1 bullet to 2 bullets. We have the morphism merge from 2 bullets to 1 bullet. We have a creation morphism from 0 bullets to 1 bullet, which we draw in this way. So the unfilled bullet, this circle, just tells us that it starts from nowhere, it creates. And we have the annihilation morphism from 1 bullet to the identity object, which starts from the bullet, and then this unfilled circle means that it annihilates there. We have these 5 generators for the morphisms in our category. Next, let us discuss the relations. Of course, just like for the category curly C, we have the corresponding relations for the crossing. So crossing squared is equal to the identity, and then we have the short braid relation for the crossing, which can be diagrammatically represented in this way. Next, we have the following relations. So if we have here creation or annihilation, we can pull it through the crossing and just disentangle them. And the next thing, we can also pull the following thing through the crossing. If we have such a diagram, we can pull this part through the crossing to have such a diagram. Remark that from now on, in order to save space, we list all the relations only up to horizontal and vertical flip. In particular, this relation would have 3 other counterparts because we can flip it both horizontally and vertically. So this picture actually describes 4 different relations, and similarly here. And it is very easy to check that these relations imply that our category P delta is a symmetric monoidal category with the same symmetric braiding as the Brauer category. So exactly these relations which allow us to pull creation, annihilation, and such kind of morphisms through the lines, they guarantee that the choice of the same morphisms as in the Brauer category makes the category curly P a symmetric monoidal category. Next, let us discuss the Frobenius relations in curly P. So we have the relations given by the following 2 diagrams. So the first diagram, you can easily see that this relation means that the split operator we can think of as co-multiplication, and this relation exactly says that this split is co-associative. And the second relation here on the right-hand side, it says that if we do the crossing after the split, we just get the split. This means that split as a co-multiplication is co-commutative. So in particular, split is a co-associative and co-commutative, and since the relations are up to horizontal and vertical flips, this also says that we have the relation saying that merge is associative and commutative as multiplication. And then we also have these relations, that this creation operator or the annihilation operator, when it is attached to a vertical line, just disappears. And then we have this relation. And all these relations combined, they say exactly that our object bullet is a commutative Frobenius object. And in particular, as we already mentioned, that it is both a commutative algebra and a co-commutative coalgebra. Finally, we have the last 2 relations. And the first one says that if we split and then merge, this should be equal to the identity. And the second one says that creation and annihilation is equal to delta times the identity of the identity object 0. So the left relation just means that the bullet object is a special Frobenius object, and the right relation means exactly that our object bullet is an object of categorical dimension delta. So this relation we also had for the Brauer category, where cup followed by a capped was equal to delta times the identity. Also, we know that the category curly P is rigid, where the adjunction morphisms for the self-dual generated object bullet are given by the following diagrams. So if we start from two bullets, we can merge and then annihilate, and this gives us a morphism from two bullets to the identity. And starting from the identity, we can create and then split. This gives us a morphism from the identity to two bullets. And because of our previous relations, it's very easy to see that these satisfy the adjunction identities. Similarly to the cases of the categories curly B and curly S, the Schur-Weyl duality can be understood as a certain monoidal functor from the partition category, where we take as the parameter the dimension of the vector space V involved in this Schur-Weyl duality. So these were the three examples of certain monoidal categories which appear naturally in the context of Schur-Weyl dualities, the classical results in representation theory. So some problems and questions at the end. Question 1, what happened to the relation that the distant transposition commute with each other in the symmetric group in the definition of the category curly S? Question 2, check with all the details that the Brauer algebra acts on V to the tensor power k. Question 3, check with all the details that P is a symmetric monoidal category. Question 4, check with all details that in the category P, the object bullet is both a commutative algebra and a cocommutative coalgebra. And question 5, check with all the details that P is rigid. Thank you very much, and see you next time.